Cool. Okay, so we're very happy to have here today to reconvene today for this second keynote lecture of the 20th DRAKKAR meeting. So we're very happy to have here with us today Ryan Holmes. Can you see my screen? Could you just Yep, cool. Okay. So
it's not on the screen, Julien.
But it should be now, right?
Okay, good.
Cool. Okay, so we're very happy to have here with us today Ryan Holmes, talking from Sydney, Australia. So just a reminder. So we've tried with the scientific committee to cover all the different ranges of scientific topics we wanted to discuss during the workshop. So touching from the use of ocean models for preparing observations. That's what we've discussed yesterday. To questions more related to the formulation and the sensitivity of ocean models, and to in a sense that's what we're going to talk about today. There again, the idea was to select a keynote presenter that could present a work that would have been published in 2021, and we were several of us very enthusiastic about the idea of giving time to Ryan Holmes for presenting his work. Ryan is I don't think you may call you an early career researcher again. I mean, still, but you Ryan did your PhD at Stanford University. Since then, you've been mostly in Sydney, first as a postdoc at UNSW, and now I understand that you've got a DRAKKAR fellowship at the University of Sydney. So all the information out there on the screen, if you want to catch up with Ryan afterwards. And without further notice, I'm going to leave the floor to Ryan to tell us more about the geography of numerical mixing in a suite of global ocean models. And the idea, Ryan, as we talked, is that you will have something like a bit less than 30 minutes for presenting your keynote, and then we'll have 15 minutes for question and answers. And with this, I'm leaving you the floor.
Thank you very much. Thank you, Thierry and Julien, for organizing this and for inviting me to give a talk. It's great to be here with you all. Now I'm just sharing my screen. Is that all visible? And can you hear me okay? Great.
All good.
Okay. So thank you very much for the invitation. I'm going to talk today about this study that we published in 2021 in James, titled The Geography of Numerical Mixing in a Suite of Global Ocean Models. So this was work that I did mostly while I was at UNSW. A lot of this was done closely with Jan, but also had a lot of input from Matthew Inglett at UNSW, Steve Griffiths in the US, and Andrew Hogg and Andrew Kiss at ANU in Canberra. Okay, so here's a little brief outline here. I'm going to start off with an introduction, then talk about the model that we used and the method that we used to quantify numerical mixing. Now, this study really came out of two previous studies that we published in 2019, looking at the global budget of heat in temperature coordinates, what I call the global diathermal heat budget. So I'll talk a little bit about that. And then we'll dive into section 4, which talks about numerical mixing and the spatial structure, looking at maps such as that one on the bottom right here. And then I'll give you a summary and talk a little bit about future work and hopefully stimulate some discussion. So let's start out with an introduction. So what is numerical mixing and why is it important? So I define here numerical mixing to be the artificial or spurious diffusion of tracer gradients arising from discrete advection. So we're going to focus on traces here. And just to make sure everyone's on the same page, we'll start with a really simple example. We have a continuous one-dimensional advection equation for a tracer theta in a direction x. Now, if we discretize this equation, in this case, using a forward in time, backward in space, simple finite difference, and we derive what's known as the modified partial differential equation for that by basically doing Taylor series expansions about the central point, then we figure out that the equation that we're actually solving is not an advection equation, it's an advection diffusion equation. Our leading order truncation error term here is second order in the spatial derivative and has this coefficient in front, which we can think of as a numerical diffusivity. And so basically we set out to solve just an advection equation. So if we take a blob of tracer and we move it to the right, we expect it to maintain its shape. But instead, what we get is we get the movement, but also a diffusion of that tracer blob. Now, obviously, modern day advection schemes are much more sophisticated than this. They're generally classed as either diffusive or dispersive, depending on the leading order truncation error term. Dispersive schemes are particularly problematic because they can create tracer extrema, which can be problems when you've got things like convection in your model. And so they're usually combined with flux limiters, which maintain monotonicity. And the main kind of result of this is most of our schemes are diffusive. And you can kind of think of this as having to come apart because the tracer must be mixed within a finite sized grid cell. So that's an alternative way to think about it. Now, the reason this is particularly problematic in the ocean is because we know that physical mixing within the ocean is quite weak, and numerical mixing can often be much larger, which ends up eroding our water masses. Now, numerical mixing has been invoked as the cause of a number of different problems in the ocean. Maybe the most obvious one is spurious heat uptake and drift. So here's a nice example of that from the GFDL's MOM6 CMIT kind of paper. So this is looking at temperature drift as a function of depth in a Z-star coordinate system. So that's where we'd expect more numerical mixing versus a hybrid coordinate system, which has isopycnals in the interior. And you can see the significant impact of that. There's other impacts, so overly diffuse tropical thermoclines and impacts on eddy dynamics that have been looked at. Now, I want to point out that this is still a problem as we increase resolution, and it particularly has an impact on how we choose parameters in global circulation models, and that's what I'm going to focus on here. So in particular, increased resolution doesn't necessarily lead to reduced numerical mixing, and the reason for that is because in geostrophic turbulence, we expect a downscale cascade of tracer variance, and so that's illustrated nicely here with comparing 4 different resolutions, kind of in a higher resolution than we get in a general circulation model, but you can see how much variance you resolve when you get down to the really high resolutions. Now, we could potentially reduce this numerical mixing to 0 or achieve numerical convergence, as I said here, by increasing our explicit diffusion parameters or our viscosities. However, this kind of concern hasn't really been incorporated into general circulation models, where parameters are often chosen ad hoc or for other reasons, such as computational reasons. Or actually, an example which is relevant to the discussion that we just had is often we're trying to reduce the viscosity because we want to increase the amount of eddy kinetic energy that we have in the simulations. Now, that's maybe a good reason, but it has potential consequences. And so that's what I kind of want to talk about here. Now, one issue with this is that numerical mixing in our model configurations can be quite difficult to quantify, and this is particularly true in general circulation models. It's generally been studied in idealized configurations, and methods that have been applied to general circulation models that generally yield only bulk metrics or rely on other arguments to get at a quantification of this. And so I guess the point I'm getting to is we don't really know how much numerical mixing is active in most GCMs, which makes it hard to make informed choices about parameters. So what we're going to do in this study is I'm going to present you a new method that we've come up with for quantifying numerical mixing, including its spatial structure in realistic general circulation models. Now, this is based on recent work that we've done. I published in 2019 in 2 papers looking at warm to cold heat transport in the ocean. So here's an example of that. This is the schematic at the end of this JPO paper, which basically quantifies the different processes that lead to heat transport from the warmest waters in the ocean in the kind of tropical bowl here to the coldest waters. And what we found in this study was that in the particular model that we were working with, numerical mixing was a big contributor to this heat flux. And so that kind of led us to this study that I'm presenting today. So what we're going to do is we're going to take this method, apply it across a suite of simulations, and evaluate the sensitivity of numerical mixing to resolution and to physical parameterizations. Now, I want to start off with 2 caveats here. So we are not going to look at the sensitivity to numerics and advection schemes. Now, that's something that's probably atypical for a study of numerical mixing, but what our philosophy basically is here is we're going to take a widely used, commonly used general circulation model and look at the implications of the choices that are already made in that model, as opposed to doing a more idealized study. Another kind of caveat that's important to keep in mind as we go through is that we're going to do the analysis in temperature coordinates. And obviously that has some good reasons behind it because we're interested in climate and these kind of heat transport processes. But it's important to note that this does not give us an exact quantification or separation between the isopycnal and the diapycnal components of numerical mixing. And in particular, the statement I made earlier about mixing being weak in the interior, that really applies to strictly the diapycnal component. Okay, so let's move on to the model and the methods. So the model we're using is the Australian Community Climate and Earth Systems Simulator Ocean Model, so ACCESS OM2. So at its core, this is a MOM5 model, and it's coupled to SICE 5.1 and forced with the Japanese reanalysis forcing. A couple of numerical details. It's a Z-star vertical coordinate model. That's really important. We're using the multi-dimensional piecewise parabolic advection scheme with flux limiters that maintain monotonicity. So we basically end up with a diffusive advection scheme. Here's some details about our momentum. So we're using centered momentum advection with a biharmonic friction operator with a grid scale dependent viscosity, which is obviously commonly used in GCMs, but has some implications that I'll talk about. And we're using KPP vertical mixing plus a background diffusivity in most configurations. And we're going to look at sensitivity across a suite of models. We're going to compare a kind of CMIT class 1 degree model, an eddy permitting 1/4 degree model, and an eddy resolving 10th degree model here. We're also going to compare different neutral physics parameterizations, so none, including the Jet and McWilliams adiabatic parameterization, and also including explicit neutral diffusion. And we'll also look at vertical resolution and background vertical diffusivity. So the method, this is basically based on water mass transformation, ideas from water mass transformation, and it's also a generalization of reference potential energy methods, which have been used previously in idealized studies, although it doesn't require resorting, which is a key fact because that's hard to do in general circulation models. So basically what we do is we construct the heat and the volume budgets of volumes bounded by temperature surfaces. So in the top right here, we pick an isotherm, say the 20 degrees Celsius isotherm, and we construct the heat budget and the volume budget of all of the water warmer than that particular isotherm, so the brown shaded regions. So that volume receives heat from the surface fluxes, so surface forcing, through parameterized vertical mixing through the base of the system, so that's vertical mixing, neutral mixing, so that's our long isopycnal diffusion, numerical mixing, which is what we're trying to estimate, and then there's also this diathermal advection term, which is associated with volume fluxes crossing the isotherm. So we estimate these different terms with F, M, and N. So these are the explicit source terms. We bin the online Eulerian budget diagnostics into temperature coordinates. And we do this every time step as the model runs in order to avoid any errors associated with time average. We estimate the tendency term, so DHTT, and the volume budget tendency term from snapshots, which is consistent with how the budget works. A kind of key advance, I guess I would say, that we've made here is that we are able to remove this diathermal advection term but by combining the heat and the volume budgets into what I call the internal heat budget. And the reason this is really useful is because the diathermal advection term is the noisy term in here. This is actually related to convergences of surface fluxes, so there's an extra derivative there. And what we end up with is an integrated budget, which is much more robust. And then finally, we estimate numerical mixing by residual from this budget. So let's look at that in a global average sense or globally integrated sense. So what we get is the internal heat budget of the model. So this is just the standard 1/4 degree simulation as a function of temperature. The surface forcing term here is an upgradient term. You can think of it like that. Basically what's going on here is surface forcing is warming the warmest waters. So it's warming everything warmer than 22 degrees and cooling the colder waters, everything below 22 degrees. And so it's acting to stretch the temperature distribution of the ocean apart, creating extreme. Now this is balanced in order to get to a quasi-steady state by mixing. So mixing is a down gradient term. It transfers heat from those warm waters to the cold waters. And so you can see in this particular model simulation, we have two mixing terms here. We have our vertical mixing in the red and our numerical mixing in blue. And so you can see numerical mixing is really significant and it's driving a significant part of the warm to cold heat transport. Now, quick aside, you'll see that the peak transport here, which is equivalent to the total amount of mixing that's going on in the simulation, which is about 1 to 1.5 petawatts. Now that turns out to be quite similar to the peak meridional heat transport. And we looked at these links in this paper in GRL, which also had implications for basin exchange. Now you might ask, how realistic is this peak transport of 1 to 1.5 petawatts? We generally think of models as being too diffuse, too much mixing. What is that like? Now that's quite hard to answer, and I'm going to show you an example calculation, but I want you to really take this with a grain of salt. This isn't published. It's just an example that I wanted to show to illustrate what we could potentially do with this. So this is taking a core air-sea heat flux product plus a World Ocean Atlas 13 SST and temperature structure product. We basically take those fluxes, integrate them in temperature coordinates using a couple of different shortwave penetration schemes. And you can see we get a total flux here profile of these red and these blue, which is admittedly quite different to the models, which is black. But the big problem here is that the core fluxes have a big mean imbalance. Fluxes are really hard to get at from observations. And so what I've done to kind of try and get around that a little bit is assume that that's distributed uniformly across the whole ocean, which gives you this gray curve. And then if you subtract that off, and I'm also, by the way, using tendency from Argo floats here, just an estimate, you can see you get something that's roughly consistent. But obviously, there's a lot of approximations here, so it's just something that I wanted to show to you. And it's kind of neat because it's a way to get at the amount of mixing that you have in the ocean from observations of surface fluxes and SSTs. Okay, so now we go on to the internal heat budget. I'll just go back to this slide and point out again how big numerical mixing is here. And just for kind of future reference, yeah, so 68% of the total, it's pretty significant. And just for future reference, the area under the curve here is a metric that I'm going to use later on. It's kind of a rough estimate of the total amount of numerical mixing, and it turns out it's equivalent to the globally integrated net heat variance dissipation rate, which is a quantity that's been used in previous studies looking at numerical mixing. Okay, so that was globally averaged. Let's look at the spatial structure. So what we can do with this method is we can extend it and look at individual fluid columns by adding a little bit of extra information. And that extra information is the lateral heat fluxes. So we add in estimates of the heat and volume flux through the side boundaries, again, accumulated online in temperature coordinates. Now that requires a few more approximations, and I'm happy to talk about those later. But practically what this means is that we get noise in the solutions, and here's an example of that. So this is a spatial structure plot that we get, looking at the Gulf Stream region and a particular isotherm. And so you can see we have little patches of red here. So this shouldn't really be occurring because red indicates an up gradient heat flux. And since we have flux limiters on our advection scheme, we would be expecting mainly down gradient schemes. And so if we do a bit of averaging in space, we get a consistent result here. And there's some other evidence that we have to suggest we're doing well here. And I just want to point out one extra thing here is that the discretization in temperature actually has no impact on this. And this is because we're using this internal heat approach, which effectively integrates up to a given temperature. And this is a big reduction in the noise that we see. Okay, so let's have a look at the results now. So again, zooming in on 3 different isotherms here, the 22.5 degrees Celsius isotherm in the top right, the 15 degrees Celsius in the middle, and the 5 degrees Celsius at the bottom here. These spatial structure plots are basically the watts per square meter of heat transport through that isotherm due to numerical mixing. And so you can see we have some rich spatial structure. We have hotspots in the tropical thermocline, particularly in the Eastern Pacific and Western Atlantic here. We have hotspots along the boundaries where we're looking at topography, and obviously in our eddying Western boundary currents and ACC regions. So let's zoom in and look at warm temperatures to start with. So I'm going to show you some longitude depth plots along the equatorial Pacific. On the left here is the numerical mixing, and on the right is the vertical mixing. And so you can see you have quite a bit of numerical mixing above the thermocline here, particularly in that region in the far Eastern Pacific. This is where you have really strong vertical temperature gradients near the grid scale. And if you look at horizontal velocity variability, specifically grid scale horizontal velocity gradients that you get here, you can see hotspots of that. And we really think it's kind of, well, this is consistent with some previous theories that when you have a noisy horizontal velocity, you get a noisy vertical velocity through continuity. If you couple that with strong vertical temperature gradients, you can have a lot of numerical mixing through vertical advection, but also you create a lot of horizontal gradients and get numerical mixing through horizontal advection as well. Now, it turns out that the mixing in these regions is strongly sensitive to vertical resolution. So we looked at this in the 1 degree simulation, comparing actually 5 different configurations. Here's just 3. So these are 2 50 vertical level schemes. The gray dots, I hope you can see here, indicates where the vertical levels are. And the main kind of point of the comparison of the top 2 panels is that the numerical mixing in KDS 51, which has much higher vertical resolution in the upper 50 meters, is much reduced compared to this GFDL 50 scheme. And then obviously, if you go to a lot more levels, so 135 levels in this case, you're reducing things yet further. If we look at this in a global integral sense, you can see we're reducing numerical mixing by about 50% at these warmer temperatures, going to that 135 level case. And you can see most of the impacts at warm temperatures in the tropics, which is consistent with where our strong vertical temperature gradients are, but there is a bit of an impact at colder temperatures. Now, since we're dominantly in the tropics in terms of these effects, and density is dominated by temperature in the tropics, we really think a lot of this is diapycnal or spurious. And I'll just point out that these changes aren't compensated by vertical mixing changes, and so we do have an impact on the temperature biases. So comparing 50 and 135 level temperature biases, they're reduced significantly when we increase the vertical resolution. Now, we also looked at vertical diffusivity. I don't really have time to go into this in detail, so I'm going to skip through it and basically just say the results are kind of what you'd expect. When you increase the vertical diffusivity, you reduce the numerical mixing and vice versa. The relationship isn't one-to-one, and there are impacts on the temperature structure, and I'll talk about that a little bit later. Okay, so let's skip through to cold temperatures. So again, looking at 15 degrees Celsius and the 5 degrees Celsius isotherms here, again, you can see that it's really dominated by these eddying boundary current regions and the ACC. And so I guess it's kind of what you'd expect here. When you have eddies, you're creating a lot of horizontal temperature variance through eddy stirring that downscales towards the grid scale. And I forgot to mention perhaps that this particular configuration has no explicit long isopycnal diffusion or horizontal diffusion. And so the only way it can dissipate those gradients is through numerical mixing. And indeed, if we look, say, at where we have really strong horizontal velocity gradients or horizontal temperature gradients, it kind of correlates with where we see these strong levels of numerical mixing. So the question, I guess, here is, does this mean that the numerical mixing is mostly neutral or long isopycnal in these regions? So to look at that, we looked at kind of indirectly, at least, we looked at introducing explicit long isopycnal diffusion. So again, looking globally integrated here, the red line in the bottom panel here is the numerical mixing in that case that I showed you on the previous slide. The blue dashed line is what happens when we add in an explicit long isopycnal diffusion, and you can see a reduction of about 60%. And that's really focused at cold temperatures. So this really suggests that numerical mixing does have a significant long isopycnal component. And I'll just point out that this kind of substitution appears more one-to-one than maybe what we saw with the vertical processes, where we don't have as bigger impact on, say, surface forcing flux. You can also add GM, which is the adiabatic parametrization, and this has a small additional impact basically by reducing the eddy kinetic energy that's in the model, that's resolved by the model. And as you'd expect, most of these are changes occurring in those eddying regions. Okay, so finally, we also looked at horizontal resolution. So generally, I guess in default configurations, what you'd expect is to have little numerical mixing at 1 degree. You'd expect it to be larger at a 1/4 degree, where you're starting to resolve some of that variability that perhaps it's only marginally resolved, and then maybe smaller again as you increase to 1/10 degree resolution. The issue with this is that we're also changing our explicit mixing, so diffusion and viscosity, as we're changing these resolutions. So what we tried to do here was come up with more equivalent configurations to compare. So we did a comparison of a 1 and a 1/4 degree configuration, and indeed we found numerical mixing larger at a 1/4 degree. It's maybe not surprising. More interesting perhaps is the comparison of a 1/4 degree and a 10th degree configuration. Now, an important point here is that we're using a grid scale dependent biharmonic viscosity. And so as we increase the resolution, we're also reducing the viscosity, which is permitting more variability. And as a result of that, we actually only see a slight reduction of numerical mixing. You can see in this kind of mid-temperature range here, about 10% perhaps, going to a 10th degree. However, if we maintain the viscosity that we had in the 1/4 degree resolution model, so we're just increasing the resolution but keeping the viscosity the same, we reduce those horizontal velocity gradients at the grid scale, and this results in a significant reduction in numerical mixing by 30 to 50%, depending on what temperature you look at. Okay, so I'm almost done here. I just want to summarize the points that I have from the results here. So basically what we did was we introduced a new method for quantifying numerical mixing, including its spatial structure in realistic GCMs. So that's the point, we're looking at realistic models here, and we applied it to temperature across a suite of simulations. Conclusions, as you've seen, numerical mixing is really significant in these models. It drives a large fraction of global warm to cold heat transport across all the configurations that we looked at. We saw there was hotspots in the tropical thermocline where we suggest it's likely diapycnal and linked to vertical resolution and vertical diffusivity, and eddying regimes where it perhaps is more isopycnal. And finally, we looked at sensitivity resolution and explicit mixing parameterizations. So that's kind of summarized here on the right, where I've got the total amount of numerical mixing on the y-axis and explicit mixing on the x-axis. You can see the red colors here indicate quarter degree models, so generally more numerical mixing. 1 degrees were less. There was a dependence on vertical resolution. There was dependence on neutral physics. As you reduce those explicit mixing parameterizations, you generally increase numerical mixing, which you can see as all of the points kind of lie on this line, going from bottom right to top left. And we also talked about dependence on horizontal resolution here. So I just want to finish up with a few thoughts to maybe stimulate some discussion. So obviously I haven't really talked much about numerics here, and I forgot to mention earlier, we really haven't focused on numerics here, but obviously that's a big factor in here. So that's a specific thing we want to keep working on. But in terms of what we found, one kind of maybe thing to think about is that we saw that increasing vertical resolution had a really good impact in the tropics, and that's relatively cheap compared to horizontal resolution. So that's something worth pursuing. And we also kind of highlighted this point that it's maybe not, at least in terms of numerical mixing, it's not necessarily a good idea to keep reducing your viscosity right to the point where you've got lots of variance at the grid scale, because you have these kind of negative consequences. And obviously this is a trade-off because there's lots of other things that are going on here. And as an example of that, just showing this kind of temperature biases in the equator from a 1/4 degree MOM simulation to a 1/10 degree MOM simulation, which has 75 vertical levels. Now the 1/4 degree, because we knew that, well, it was suspected that there was a lot of numerical mixing in this, we were using a 0 background diffusivity. As we increased the resolution, we actually saw the biases get worse. And this was indicating that we were decreasing numerical mixing to the point where we actually needed to add in extra physical mixing to compensate for that. Now, I've been tiptoeing around this point. This is maybe a question for discussion. Does numerical mixing constitute a valid representation of absent physical mixing? Now, the argument here might be that if you reduce your explicit mixing, so explicit diffusion, you lead to more numerical mixing, but you lead to less total mixing overall. And if we're really concerned with how much total mixing we have, maybe that's a good approach to take. And this is used in implicit LES approaches, so it's not completely foreign. Obviously, it's not physically controlled in the sense that we don't set the diffusivity, and so that's maybe something to consider. And then the final slide here, just a little bit looking forward to what we're going to be doing in Australia. So in Access OM3, which is the next version of Access that we're going to work with, we're looking at going towards MOM6. And so Andy Hogg gave me these nice figures. He's got a pan-Antarctic 20th degree simulation as kind of a precursor to Access OM3. And he's done a comparison comparing geopotential vertical coordinates. So this is looking around Antarctica to a hybrid vertical coordinate, which uses isopycnals in the interior. And what we found in these simulations is that you maintain the circulation. So these models are really good at producing Antarctic bottom water, but the geopotential vertical coordinate mixes that out a lot more rapidly as the bottom water kind of descends down the slope, whereas the hybrid vertical coordinate is able to kind of maintain those properties for longer as it moves into the mid-latitudes. And that actually gives us a stronger bottom water cell, which is something that a lot of models have problems with. So a little bit of future work here. There's some issues about how you choose the vertical levels. So you can see on the top right here, we've got quite low resolution in this kind of mid-layer level. That's maybe something we'd like to address. And there's also an issue with what density variable we use. These are based on potential density, but we know that's not exactly neutral. And so there's some work to be done, particularly perhaps with Trevor McDougall and Jeff Stanley, who's at UNSW. We have some ideas about working on some potential advances to this and looking at numerical mixing at the same time. Okay, so that's it for me. Thank you very much for listening. I hope I told you something interesting, and I'm happy to respond to any questions or comments that you might have.
Thank you very much, Ryan, for this talk, and I think we can thank and applause for this really nice talk. And once again, right on time, so that's perfect. We're doing good time-wise, and we have several questions to start with. I think Alex, Megan was first, and then we have Arno, and then Bob, and we'll see how far we get then. So Alex, please.
Hi Ryan, great talk. I enjoyed your paper last year. I was interested in what you presented for the tropics, for the warm water regime. I haven't looked much at the tropics in my analysis, and I was wondering if you had any thoughts about what was creating the numerical mixing along the equator, because that's a very active region dynamically. You've got a lot of tropical instability waves. You've got the wind forcing that Adam Blaker and Mike Bell published recently. So is it horizontal or vertical advection mainly? Because you've got that strongly sloping thermocline, or is it advection by transient motions?
That's a really good question. And by the way, thank you very much for the comments. I enjoyed reading your paper as well on this same subject. So I think I have another slide here. So I think what's going on here is we have a lot of horizontal velocity variability near the grid scale. And so this is indeed likely associated with tropical instability waves. It's getting down to the grid scale, perhaps because of our viscosity choices. You can see that in this panel here on the left. Now, whether it's horizontal or vertical, we cannot say exactly from these diagnostics. Our advection scheme is three-dimensional, so we don't actually have a separation there. I suspect it's a bit of both, but the source of it is the vertical gradients. So when you have that noisy horizontal velocity, you get a noisy vertical velocity, and it's acting on the vertical gradients there that gives you also strong horizontal gradients through the vertical advection. And so I think it's potentially both, but again, we can't say exactly how much is each. And maybe that's not even a well-defined question, I guess, with the three-dimensional advection scheme. But what we do find in particular is that really strong sensitivity to vertical processes, vertical resolution, vertical diffusivity.
Yeah, what you say about grid scale noise is really interesting, because I don't know if you've seen the paper that I wrote with Dave Storkey last year about the effect of viscosity on numerical mixing. But we found it was strongly correlated with the grid Reynolds number.
Yeah, so we looked at the grid Reynolds number as a metric, and I think it definitely works if you're looking at comparing different simulations, but we actually found that it wasn't very good for kind of identifying spatially where the regions of strong numerical mixing was. And I think that's for two reasons. One, it doesn't contain a measure of temperature variance in it, it's just velocity variance. And two, at least the one I looked at was based on total kinetic energy, not an estimate of velocity variance at the grid scale or velocity gradients. So perhaps if you kind of introduce those elements in there, then it might give you a better estimate. So we didn't put it in the paper just because it wasn't very representative. So we just focused on the variance of temperature and velocity itself.
Thank you.
Thanks for those. Thanks for this first exchange. We then have a question by Arne Blastok.
Yeah, hi Ryan, great talk. I really enjoyed that. I have a question on the difference between the upper ocean and the deep numerical diffusivities. I mean, if you is it possible to put a time value on that? Or in other words, if you would set up an ocean model and have for computational reasons a fixed number of vertical levels, could you use your methodology to rate if you invest those levels in the upper ocean or in the deep ocean?
You can definitely do that in terms of, well, I mean, that method would tell you what the sensitivity is. I mean, it's I guess an example of that is in the tropics. Again, it's not going into the deep ocean because that's not something we really focused on. But you can see, obviously, that depending on where you have the vertical levels, so this was both 50 vertical levels. If you have it all in the upper surface, then you reduce the numerical mixing there. It actually turns out, interestingly enough, that comparing these two simulations, I think you can see that here, you actually have less in terms of a global mean numerical mixing in the GFDL 51, and that's because you actually better resolve kind of the thermocline region in that region. That's where the strongest fluxes are. Now, I guess one important thing to point out, and that maybe people have noticed here, is that the metric that I'm using to quantify numerical mixing here is a flux. It's not a diffusivity. And I think that has an implications for whether you're talking about the surface ocean or the deep ocean. Now, the reason we used a flux is because it's actually the objective quantity that you want to look at. And this is what most of the methods use. If you go to a diffusivity calculation, you have to figure out what gradient you're going to use. So resorting is one way to get to a gradient, but that obviously is problematic. You have time averaging issues. So we decided to stick with this kind of objective metric. And we could definitely look at the interior more. You're just working with weaker fluxes.
Okay, thanks.
Thanks for this exchange. We then have a question by Bob Alberg.
Yeah, thank you very much. I enjoyed the talk, Ryan. I'm actually going to change my question. So because you've worked with the flux instead of the diffusivity, we don't entirely know what the fluxes are. We have published estimates of the diffusivities. Do you have a way of normalizing the fluxes, or conversely, actually going back and using the diffusivity to estimate the spurious mixing as a ratio to the physical mixing? In other words, something where we're normalizing it to something where you say you'd like this to be a small number compared to 1, as opposed to something with arbitrary units that we sort of know what it looks like, but maybe a little bit less informative to people who are not quite so familiar with the details of mixing in the ocean.
Great question. So this is something we tried to do in the simulation. So one way to think about it is, if we're in the situation where we have only a vertical diffusivity in terms of our explicit diffusion, if we divide the flux through the isotherm due to numerical mixing by the flux due to vertical mixing, and we assume that numerical mixing is vertical, then we get the same as if we were taking the ratio between the diffusivities, right? Because the gradients are the same that they're acting on, right? And we did actually looked at that, and you can look in the interior and you can see, yes, there's more, that coefficient is greater than 1, as you said. The issue comes when you try and do that in the eddying regimes where you have a long isopycnal numerical mixing, or what we think of as is a long isopycnal numerical mixing, because then the gradients are very different, right? And so it doesn't really make sense necessarily to divide the two, because one's coming from vertical processes and one's coming from horizontal processes. So we did originally have that figure in there, and then we thought actually this only really makes sense in the tropics where we think it's mainly vertical. So maybe that's an issue that you could, or we would hope to address when we go more to the density coordinate thing and the temperature coordinate, where it might be more relevant.
So in that case, you could normalize it by the total of the physical mixing. Do you have maps of that normalized, that ratio? I know you have quoted overall values of 65%. As kind of a global mean. Do you have maps of that fraction?
So I made the maps. The issue, I guess, with the control simulation is you're dividing by 0, because we have no explicit or long isopycnal diffusion, right? So I didn't really try and play with that. I mean, I guess we could look at it in the case that did have an explicit diffusion. Yeah, you'd have to be a little bit careful with your gradients, I think, as well. But that's something to consider, I guess.
Okay, thanks for this exchange. We now have a question by Adrian New and then Mike Bell.
Hi, Ryan, very nice talk indeed. Just a philosophical point, really. I think your analysis was based on doing a diathermal budget and a volume budget. Did you think of doing a diapycnal budget instead of a diathermal one? And would your results have been any different had you considered cross-isopycnal sort of mixing rather than cross-isotherm mixing?
Yeah, so that's something we'd really like to do. The problem with density, well, there's a number of problems with density. One is that the model is actually not solving an equation for density as much. It's solving a tracer temperature and salinity equations. And so it's a little bit harder to construct the budgets. And we lose some of the nice properties that we have with temperature. The other issue is that we run into what density variable do we use? So commonly we use potential density, but that if we're using, say, potential difference reference to the surface, we know that that's not very neutral in the interior. or potential density reference to 2000, that only works at 2000 and we're moving things up and down. Now, that's not to say it's not possible, and we're definitely looking at that. And I'm hoping to work with Jeff Stanley and Trevor McDougall, who know a lot more about these issues, to extend this method to density. But there's some issues, basically some technical issues, I guess, that you would say there that meant we focused on temperature in this case.
Okay, thanks, Ryan. Yep.
Thanks for this answer. Mike Bell, you have a question about isopynyl mixing, right?
Yeah, thank you, Julien. And thank you, Ryan, for a really nice talk. It's very interesting, important work. You mentioned actually towards the end of your talk about this issue that with large eddy simulations, the numerical mixing is often viewed as a sort of substitute for physical mixing. And I wonder to what extent you can reduce the numerical mixing by using appropriate amounts of isopycnol mixing or perhaps other direct parameterizations.
Yeah, so as I talked about here, we do indeed see a reduction in numerical mixing when we add our long isopycnol diffusion. So that's actually comparing the red curve here to the blue curve here. And this is potentially, there's some promise here. The issue, I guess, is, and this comes back to that comment that I made at the end, this is a good thing to do. We reduce the numerical mixing, but we actually introduce extra mixing, I guess I would say. It's likely that the total amount of mixing that we get is higher than we would if we just let the model mix numerically. At least that's the argument that we have. And so I guess I can't really answer that question. It's an open question, I would say, about which one's better to do. And I guess I'll also point out that this was really relevant in the discussion that we just had before my talk. We were talking about stochastic variability in these models. That's one thing you're really interested in getting these models to represent. And so that's one reason to reduce your viscosity, but that has negative consequences. So there's all of these decisions that you have to make that are balancing different constraints that you have. It depends on what you're interested in. Are you really interested in getting lots of variability in your model so you have good stochastic spreads or ensemble spreads? Or are you more interested in making sure that your water masses in the interior are really, really maintained as best as you can? I guess this is the issue we have with models. We're trying to do multiple different things with them. And depending on what we're doing, we might want to make different choices.
Thank you.
Thanks for this. One more question by Thierry Pendef.
Hi, Ryan. Thanks for this talk. Very interesting. I just had a very simple question. I think it's a simple question related to what Adrian mentioned. The advantage of density is that basically it's monotonic everywhere. It's not the case of temperature at high latitudes. How do you deal with that?
So the dependence, in our method, we're just spinning in temperature. We're not caring about vertical gradients. So basically I'm saying that the fact that temperature can be inversely stratified with the vertical dimension has no impact on our method. We're not doing a resorting. We're not doing those kind of dividing by vertical gradients in any sense. We're just spinning into temperature coordinates. So it's completely general with respect to that. I agree, neutral density is more vertically stratified generally, but actually with respect to our method, that doesn't have any impact.
Well, but if you have, for instance, off the Antarctic coast, cold water, warmer water, and then again, the same cold water.
Yes.
Do you blend the two cold waters in the same category and you don't care about where it is?
Sorry, so you're exactly right. So what we get, and this is probably something I should have pointed out, all of these maps are made on isotherms, and that's fine if you're looking at a horizontal structure. If you're looking at a vertical structure, say like this, the way I'm actually plotting this is I'm plotting it, the field is calculated on temperature coordinates, and then I'm plotting it using the annual mean position of those isotherms. So in terms of the metric itself and the measurement, there's no issue. When you come to plot it and actually link it to where it's occurring spatially, then you have to make a decision. And so if you went close to the Antarctic coastline, like you said, you wouldn't be able to differentiate the spatial position in the water column if you had that same isotherm in two different positions.
Okay, thanks.
Thanks a lot. I will take also the opportunity for question, if I may. I think you made a very interesting comment, Ryan, when you raised the point that we tend to consider numerical mixing as something spurious, something that is wrong and that we want to get rid of. But in some circumstances, we're very happy that this numerical schemes can help us compensating for closures, and there are even like fields that you mentioned, like the eyeless approaches, where you use your numerical schemes for mixing. So if we were to accept that a fraction of that spurious mixing is okay, what would you recommend as an overall rationale for deciding what fraction we should keep, and how to comprehensively approach that question given the other source of errors and closures in the models?
That's a good question and a difficult one to answer. I guess I would start off by saying what you really need is you need to know how much mixing is in your model. And then you can use that to kind of guide what your decisions are and what the impact has on the solution. In terms of what's acceptable, I mean, yeah, the issue with numerical mixing, right, is that it's not physically controlled. We don't actually set the diffusivity. And so if we can be confident that it's giving us something that we think is controlled to some sense, then that's probably okay. But I guess we just don't really know what the impact is in that sense. Yeah, I can't really answer more than that. I think it's a tricky question. It's great to have quantifications like this. There's lots of different metrics we can look at. The more information we have, the better we can make these kind of decisions.
Good news is there's ample room for more research on this. So with this, I'd like to conclude and thank you again for this great presentation, Ryan. And thanks for staying up late at night there in Australia. We would be very happy to have you with us for the rest of the day, but I imagine that you will probably collapse at some point. But thanks for joining us. As we said, the recording will be available to all the meeting participants, so don't hesitate to go back to this. And if you want to join us tomorrow, Ryan, you're more than welcome. Thanks a lot.
Great. Thank you very much, and thank you for all the questions and the interaction and the discussion. It was great.
Cheers.